Hello everyone, we are pleased to be able to welcome you to our speech. Today, we are here to give a presentation on capsule networks. Capsule network is a new neural network proposed by Jeffrey Hinton. It is based on a new structure capsule, which is combined with the existing convolutional neural network to achieve very superior performance on some image classification data. First, I will start with the timeline of the capsule network. Hinton proposed the first paper on the prototype of capsules in 2011. The purpose is to include the position information and pixel information in the image into the capsule. In 2017, they proposed the first version capsule network connected by dynamic routing, which uses a set of vectors to characterize a certain feature in the image. He proposed the second version capsule network in 2018, replaced the vector with a matrix. In 2019, stacked capsule autoencoders used unsupervised learning. Its main principle is to use an autoencoder to segment paths from an image, and then combine the paths into an object. Maybe you will have a question. Why should we pay attention to the development of capsule network? I will answer it for you next. From 2011 to the present, convolutional neural networks have been widely used in various image recognition tasks, but there are still several problems. The first is that when the image subject does large translation and rotation, the network's accuracy will decrease. This requires us to enhance the training dataset, such as copying many images and change the angle or position. Another problem is that the convolutional neural network can find the detailed features in the image well, but it is not sensitive to the relative position of these features. For example, the lady in this photo, after changing the position of the eyes and mouth, the network can still recognize her as a person, because the pooling layer in CNN has lost the information about the precise position of the entity. Therefore, researchers want to develop a new structure that can replace the pooling layer. The capsule network is inspired by the human eye recognition mechanism. Each capsule represents a feature of an area in the image. The upper capsule gets a large area but combines these features. Finally, we can reconstruct the image by the output value of the capsule and change one of the values to see changes in certain characteristics of the image. Before explaining capsules, let me introduce two important concepts. The first is viewpoint invariant, which means that when we observe an object, a certain characteristic of the object does not change with the change of viewpoint. The relationship between object and its part is constant, while the relationship between object and observer is equivalent. For example, it will become smaller when we are away from the snowman, but the ratio of the volume of the two spheres above and below the snowman is constant. When designing the output of the capsule, we hope that it not only represents the probability of a feature is present, but also contains some attribute values of the feature, such as the curvature and the length of a curve. In the first version of capsule networks, researchers used the length of a vector to represent the probability of a feature appearing, and the components of the vector to characterize the attributes of a feature. The upper layer capsule represents a larger range of features in the image and is composed of lower layer vectors. Therefore, a mechanism is needed between the two layers of captures to assign these features to the upper layer captures, and the feature vectors are represented by weights in the captures. For example, in the following example, the upper capture has four types of cat: parrot, goose, and dog, and the lower capture is feather and tail. Cats and dogs do not have the feature of feathers, so their weight is 0. Both goose and parrot may have this feather, and their weight is 50%. This table is a compression chart of the calculation process of the capsule and the traditional neural network. The capsule network inputs a vector UI. First, multiply the input vector u by the matrix W, so that the dimension of the vector can change to the same as the upper capsule, and it also represents the relationship between the upper and the lower features. The matrix W can be adjusted by backpropagation during training stage. Then the vector is weighted by C and summed to obtain S, where C is routing coefficient and iteratively obtained by the routing algorithm. Finally, the vector V is output through a nonlinear function. The squish function is specifically designed for this purpose, and it can comprise and normalize the output vector.
The detailed process of the dynamic routing algorithm is given below. This is an iterative process. Multiply the input vector by the matrix W to get the prediction vector U. Look at the fifth line. Vector U multiply the weight C and then sum linearly. Calculate the output vector V of the capsule. At the seventh line, the correlation B of each component is calculated by the dot product of the component U, and the output V in the weight C is updated. When the angle between U and V is small, it indicates that the correlation is strong. Finally, the upper capsule gets a combination of several strongly correlated vectors specified by the lower layer. As shown on the right, the 8 prediction vectors are concentrated into 3 distinctions and combined into 3 upper layer vectors. The process is similar to the k-means clustering algorithm. This is an example of a handwritten digit dataset given by the researcher. First, the convolutional layer performance, preliminary image segmentation, and feature extraction. Then use 2 layers of captures for classification. The second layer of capture output 10 vectors with 16 dimensions represents 10 numbers. Each dimension corresponds to a center attribute of a digital image. We consider these 3 layers as an encoder. The next 3 fully connected layers are decoders, which are store handwritten digits based on the vector output by the capsule. This is a demo program. As you can see, changing the value of an element in vector can change the slope of this number. We can even set a vector out ourselves and let the network generate a digital image. This is the interoperability of the capsule network. In the second generation capsule network, the researcher replaced the vector with a matrix and an activation value. The matrix becomes pose. So what's the difference between a 4x4 matrix and 16-dimensional vectors? The elements of different positions of the matrix have different importance, and the importance of each element of the vector is the same. The position of the diagonal elements of a matrix seems to be more important than the other elements from a calculation perspective. To transform a 16-dimensional vector into another 16-dimensional vector, we need a 16 by 16 transformation matrix, while a 4x4 matrix just need another 4x4 transformation matrix, so it reduces the number of parameters. At the same time, we also need an attribute in the matrix as the activation value. Here is it. The two beta in this formula are parameter adjusted by back progression, and the cost calculates the information entropy of the matrix.
We often use Gaussian distribution in statistical distributions. It has two parameters, expected value and variance. By adjusting these two parameters, the data distribution is fitted. When the data distribution appears to contain multiple subdistributions like multiple spikes, and the data can be better covered by linearly overlapping, theoretically, an infinite number of subdistributions can be combined into any shape. There are three sets of parameters involved in the formula. Pi represents the weight of a subdistribution, mu is the expected value of this subdistribution, and sigma is the covariance of this distribution. The fitting process uses the EM algorithm to iteratively update these three sets of parameters. In the capsule network, we use pi as the root between the capsules to represent the probability that a lower layer feature belongs to an upper layer feature. For the upper matrix Mi, each element in Mi corresponds to a mixed Gaussian distribution. Each capsule in the lower layer corresponds to a subdistribution. The input matrix is first multiplied with the transformation matrix to get the volt matrix. Think of the matrix as a volt vector V, which has the same dimensions as the upper matrix. For all vectors V, each element in V corresponds to a Gaussian distribution. This distribution is fitted by the upper matrix M from all the vectors connected to it. Consider the probability distribution of each element of the matrix Mi. The value of the upper matrix is the expected value of these distributions or the cluster center. Looking back now at this formula, PJK represents the probability distribution of the number K element which in the number J upper matrix. The process of EM initialization is divided into two steps. First, Rij is initialized to distribute the weight evenly. In step M, the expected value and the covariance of each element of the matrix M based on the distribution of Rij are calculated. Then calculate the activation value of the upper matrix. In step E, all the elements of the input vector V are substituted according to the probability distribution of the currently obtained elements. To obtain the probability that the vector V belongs to the upper capsule, based on this probability, the routing weight R is calculated, repeated multiple times to make the probability distribution converge. Finally, the expected value is taken as the element of the upper matrix. The research built a 5-layer capsule network for testing. The convolutional layer is still used for the bottom feature extraction and input to the primary caps layer. Following is the 2-layer convolutional capsule layer. Their connection is similar to the convolutional layer sharing the W matrix, but the EM routing is used to calculate the capsule output. Finally, output to class capsules. Each capsule represents a class. The capsule with the highest activation value is used as the output of the image. Here is our result. As the baseline for the experiments, the researcher also trains a CNN which has 2 convolutional layers. The CNN baseline achieves 5.2% test error rate and has 4.2 parameters. We deduce that the size CNN 2011 network has 2.7 m parameters. By using small matrix multiple lines, we reduced the number of parameters by a factor of 15 to 308K compared with our baseline CNN. In order to test the generalization ability of the capsule network and compare it with CNN, the searcher extracts some perspective images from the training set of novel viewpoint sets. The rest is the familiar viewpoint set. The two networks were trained to achieve the same error rate in the familiar viewpoint set. The performance of the capsule network in the new perspective is significantly better than CNN. Finally, it's our conclusion. Researchers successfully generalized this concept to metrics after the vector capsule network was proposed. This change drastically reduces the number of parameters to be trained. EM routing combines features through a Gaussian mixture model. Compared with dynamic routing, this can better distinguish the coupling coefficients of different features, increasing the degree of non-linearity. The iterative process has been tested to become faster. It only takes 3 iterations to coverage to good results. Enhanced generalization capabilities combined features achieve rotation and translation invariants. It is more robust and performs well against white box attacks. But for black box attack performance, it's similar to CNN. This is our reference. Thank you for your listening.